Welcome back to the fifth part of the third week, where we are talking about dynamic programming paradigms for solving problems. In this video and the next one, we will talk about optimal binary search trees. So you've probably seen the BST data structure before. This time, just like we did in file storage, we are going to look at a situation where not only do you have a bunch of keys that you want to store, but you also know how frequently you want to access them. So normally, if you remember how you approached binary search trees, you must have spent some effort in trying to keep them balanced so as to ensure that when you're storing a set of n keys, you encounter or you create a tree of maximum depth being something like log n, and this will ensure that when you are doing your searches, you never suffer a cost of more than log n. So the cost of every search is worst case log n. But now we are in a slightly different situation where we have a set of keys and we also have a set of frequencies that are associated with those keys. So let me make this explicit here. So the input is a collection of n keys. Along with associated frequencies. So let's say that the keys are stored in an array A and the frequencies are given to us by an array F, right? Now the total cost of a binary search tree that you build is going to be basically given by the amount of time that you need to access any of these keys weighted by its frequency. Okay, so we're going to say that for accessing the ith key, the cost is going to be f of I times the amount of time that you need to discover the key in your BST. So that's essentially the number of ancestors So this is basically how much do you need to climb down in the tree to be able to find the key. So that's the number of steps you need for discovering the key, but you have to do this f of I many times. That's the frequency associated with that key. So the total cost is basically the cost of discovery weighted by the frequency of access. And this should feel familiar if you have looked at the file storage problem, because there we were doing something similar, except our storage structure was linear, so we didn't have to worry about a binary search tree hanging around in the background. But now we will have to find an optimal tree structure for these keys so that we optimize our overall cost. I'm assuming that you have seen binary search trees before. If not, the course notes will have pointers where you can find out more about them. So I'm going to not get into how to build balanced binary search trees or binary search trees in general. But the one thing that's worth recapping is that the key property of a binary search tree is that it's a tree which stores a key at every node, with the property that if you are at a particular node, you have two choices. You can either go left or you can go right, and all the keys that are stored in the left subtree are going to be smaller than the key that is stored here at the root. And if you go to the right, you're only going to get keys that are larger. So typically the way the search is going to work is you look for your key at the root. If you've already found it, then you can go party. That was incredibly lucky. But typically you would have not found your key, but then you compare your key with the root, and if it happens to be larger than the root, then you go into this right fork. You say, I'll explore further in the right subtree, and if it happens to be smaller than the value at the root, then you go left instead. So that's how binary search trees work. Once again, this is just a very quick recap. If this is your first encounter with BSTs, please make sure to look them up. And if you're a bit rusty on your memory of BSTs, again, please do revise the material from the course notes before progressing further in this video. Okay, so as we said earlier, what we are looking for is a BST that minimizes this total cost. That's the desired output. Now I will just focus on actually calculating what the minimum cost is. Again, you can actually construct the BST by backtracking through the DP table, and that's again something that I will leave as an easy exercise. So before we dive into thinking about what are the subproblems and what kind of recurrences should we be thinking about, let's just do a couple of small examples to get the hang of what is happening. So suppose our keys are just 10, 20 and 30. And now let's also put down some frequencies to go with the keys. So let's say 10 is accessed with a frequency of 5, 20 is accessed with a frequency of 1, and 30 is accessed with a frequency of 25. Now I've deliberately put down some very different looking frequencies here just so that I can dramatize the difference in costs between differently structured BSTs. So to begin with, let's try to draw out a balanced BST for this. There are three numbers here, all distinct. A typical balanced BST would want to put the median element at the root. In this case, this happens to be 20, and we're going to get 10 on the left and 30 on the right. Okay, so what's the total cost of this BST? Well, at the root, the cost of accessing the element is just 1, because remember that the cost of accessing an element is counted as the number of ancestors, and at the root, the only ancestor of the root is the root itself. And that's the convention that we are going to follow. So we just pay a unit cost of access for the element 20, but we are going to weight that by the frequency with which 20 is accessed, which happens to also be 1 in this case. And for 10, the cost of access is going to be 2, because you'll have 2 steps to get to 10. You'll have to go through the root and then read the location at 10. So that's going to be 2, and the multiplier is going to be 5, which is the number of times that we do this. And finally for 30, it's again going to be 2, and the multiplier is going to be 25. So you might already be having a bad feeling about this cost here. So the total cost turns out to be 25 times 2, 50, plus 5 times 2, 10, plus 1, so that's a 61. Now, can we do better? And it certainly feels like we should be able to, because somehow we have associated with the root, which you can think of as a premium slot, the element which is actually accessed the least. So even intuitively, this just feels a bit off. Let's see if we can do better by positioning the most frequently accessed element as the root. So that would be 30. So let's see what happens if we put down 30 at the root. Well, to build out this BST further, we could either try to insert 10 first and then 20, or the other way around. Let me try to insert 10 first, because again, there's some intuition about this being the next most frequently accessed element, so I want that to be as close to the root as possible. 10 being less than 30 will land up on its left, and then finally we have 20, which will end up as the right child of 10. Now, of course, we are using a greedy approach here, which is not going to be our final algorithm, but for this small example, it sort of makes sense to pursue our instincts a little bit, just with the goal of getting a tree that looks better than the one that we've just built out, which has a cost of 61. All right, so what's the total cost going to be here? At the root, we have 30, which is nearly free to access with a cost of 1. And that's going to get a multiplier of 25. And then for 10, we have access cost of 2. And the multiplier is going to be 5. And for 20, we have an access cost of 3, which is something we did not encounter at all when we were doing the balanced variant. because the depth was only up to the first layer of children. However, here we do experience a cost of 3, but fortunately the weight associated with this access cost is just 1 because the frequency of 20 is just 1. So what does this add up to? Well, this adds up to 25 plus 10 plus 3. So that's 25 plus 13, which is 38. And you can see that that's, well, almost dramatically lesser. You can increase the gap in the costs of these two BSTs by simply ramping up the frequency of the element 30 out here, just to get a sense of the fact that the structure of the BST really matters. And when you're usually learning about BSTs, we put in a lot of effort into making them balanced, but once frequencies come into the picture, balance may not be the most crucial thing. It's really about trying to make sure that the more frequent elements are closer to the root so that you have a more optimized cost overall. Now, unlike file storage, where we could sort of get away with a greedy approach, here you can think about whether a greedy approach will serve you well or not. But our discussion here is going to now steer into coming up with a dynamic programming based solution for this problem. So now that we've looked at a couple of examples, let's come back and look at our cost function, which is what we are trying to optimize. So I want to look at the cost of a binary search tree T that's associated with the keys in A, and let's say the frequency array is given to us as F. Now for convenience, I'm going to assume that the array A contains the keys in sorted order. So that's just going to be convenient as we break down our recurrence. So let me make a note of that here. So now when we think about the cost of the tree T, I want to break this down. I mean, of course, what we know originally is that this is the cost associated with each key. We have the cost of accessing the key being the number of ancestors that it has. And this is weighted by the frequency of access. So you can think of this as these two components. This would be the access cost, and this here is the frequency of access. Now I want to think about this cost as being broken down into two parts based on where these keys are in the tree T. Because looking at it that way will help us inspire ourselves into discovering the correct set of subproblems to actually find the optimal BST. So how can we think of this recursively? Well, let's think about how these costs are adding up. So we have some element here sitting at the root. Let me say that that's A of R. Let me denote the index of the element that's sitting at the root by R. And then we have the left and the right subtrees. So let me call this TL, and let me call this DR. And notice that the root is actually an ancestor of every element here, right? So the root is going to contribute to the access cost of all the keys. So I can pull out a 1 from this sum and basically account for the contribution of the root to the total cost, which means that once I've done that, I can sort of throw away the root because I've accounted for how it's contributing to the access costs. And now I'm left with these two smaller pieces, and I can worry about them and in recursion essentially, right? So now the elements that are sitting here and the elements that are sitting here, I can think of them in terms of the ancestors that they have in these subtrees as opposed to the entirety of the original tree, right? So let me rewrite this cost function and you can think about whether it makes sense. So first, let me write down the cost as contributed by the root. So the access cost contributed by the root. So every element that's going to be accessed f of I many times, it has to, in some sense, go through the root. So that's just all the frequencies added up here. So this allows me to separate the root out and say that, okay, now, we don't really care about the root anymore. We can delve into the subtrees. And remember that we were looking at a sorted array of elements. And the root was somewhere here. So we know that all of these elements are going to go into TR, and all of these elements here are going to go into TL, because that's just the structure of a BST. Everything smaller goes to the left, everything larger goes to the right. So the cost here can be broken down further as, well, essentially the cost of access within those subtrees. So I want to look at all the keys from 1 to R minus 1 and look at their frequencies, and now multiply that by the number of ancestors of AI, but this time in TL, not the entire tree, because the root as an ancestor has already been accounted for. And similarly, we can also look at the right hand side of the array, which ranges from R plus 1 to N. And here I have the frequencies multiplied by the cost of access, but this time in TR. So that's the total cost. And feel free to pause here for a second to make sure that you are convinced that that's indeed what is happening, right? So for the root element, notice that you only pay a cost of the frequency of that element because you practically get it for free. The access cost is 1, so the root is just, its cost is fully accounted for by f of r sitting as a part of this expression here. For everything else, we have broken down the cost into two components. One is the cost of traversing the root, and then it's basically the rest of it, which is now being pulled out by our recursive expressions here. So notice that these summations that we have written here are really just cost functions on their own right on smaller BSTs. So we can think of this as the cost associated with TL for the frequency array, but now it's not the entire frequency array, it's just the frequency array going from 1 to R minus 1, and the cost associated with the BST TR with a frequency array of R plus 1 up to N. Okay. So I hope this method of breaking the cost down makes sense. And now when we want to find an optimal BST, right? So remember, back to the drawing board, all you have is the two arrays, which is the keys array and the frequency array, right? This is what we are looking at. And now we want to build a BST that optimizes for the total cost. So what is the best way of thinking about this? At least one way, which I think is fairly reasonable, is to say, let's think about what element the optimal BST chooses as the root. Again, this is something that we don't know, but we can make a guess by simply trying out all possible elements. So I don't know which element is the root, but I can try everything out. So what I would be interested in knowing is, if I chose the ith element as the root, then what's my cost going to look like, right? So I'm going to basically try all possible ways of breaking things down from here. But for this to actually work out, what are the sub problems that you're going to generate? Well, if I say that I is the root, then I'm going to break this up into everything from 1 to I minus 1 and from I plus 1 up to R, right? So it seems like we do need to understand from our subproblems, we need to understand what's the best BST for the first I minus 1 elements and the suffix which begins at the I plus 1th element. We need to have information about these things so that we can pull it together. But when you zoom in to this left subarray here, and you're working with the subarray that starts at 1 and ends at I minus 1, and here you try to again second guess the root. You will say, okay, suppose this was rooted here at, let's say, some index j, then once again we need to understand what's going on for the subarray which begins at 1 and ends at j minus 1, and the subarray which starts at j plus 1 and ends at I minus 1, right? So our subproblems are basically turning out to be subarrays of the original array, right? If you basically try to break it down in this particular way. So think about how will you set up your subproblems. What should your recurrence look like? I think we have thrown in here enough hints for how you might want to build it up. So I think this is a great place to pause and figure this out as a bit of an exercise. However, we will come back and discuss the rest of this completely in the next video. So I'll see you then, and good luck figuring this out.